We have taken a look at the Nyquist criterion or Nyquist test for stability of a closed loop feedback control system, and we saw that the criterion or test involved plotting what is called the polar plot or the Nyquist plot for a system, which is essentially the frequency response of the system, or rather frequency response of the loop transfer function kgh. What do we mean by frequency response? We mean the following: apply a sinusoidal input, and in the steady state the output will also be sinusoidal, but of a different amplitude and different phase. So, the gain or the ratio of the amplitudes and the difference in the phase is what is measured or calculated knowing the transfer function of the system, and then it is plotted to obtain what is called the polar plot. Now, this is an example of what are known as frequency response methods or frequency domain methods. It involves frequency response, involves the idea of a sinusoidal signal or a input and response to such a signal. So, methods like this are known as frequency domain methods. And as I told you earlier, these methods were developed starting in the 1930s because of study of and problems associated with amplifiers. And in the case of amplifiers, the sinusoidal signal was a very natural input candidate. These methods were applied to control system problems because it was in fact the other way around. The idea of feedback was used in amplifier design to stabilize the amplifiers, as we saw earlier. So, that was the contribution or gift from control systems to amplifier design, the idea of feedback. And then in the other direction, the idea of frequency response was contributed by amplifier study to control system study. And naturally, therefore, a large number of people worked on this problem and associated ideas, and a whole range of techniques known as frequency domain methods or techniques were developed. And we have only looked at one part of it, which is essentially the Nyquist criterion, and then of course, because it requires the frequency response, we looked at Bode plots, that is a quick way of obtaining an approximation for the amplitude and phase variation with frequency. Now, the subject was developed further along the same lines, but we do not have time to look at all of that. Moreover, what was perhaps very appropriate and natural in the 1930s and 40s is no longer necessarily appropriate today. And so, in my opinion, one does not need to spend that much more time on frequency domain methods. However, there are some interesting engineering ideas, that is, ideas which have what one may call an engineering aspect rather than a purely mathematical aspect or a purely physical aspect, and therefore we will spend a little more time looking at some of those ideas. I have not gone into any detail of design of compensators using the frequency response method. I just mentioned some compensating networks and left it to you to find out their transfer function and also find out their frequency response. One of the things that people tried to look into and tried to develop techniques or formulas was the relationship between frequency response and what may be called time domain behavior or time domain response. In particular, response to inputs like step input, one talks about the step response, response to a ramp input or response to a pulse, very often what is called a rectangular pulse, a single pulse of this kind, or a response to a square wave input and the like. Now, a step input of course has nothing to do with periodicity. It is just a signal which starts at some time and then keeps on being at a particular level for all time to come. a pulse appears only for a short time and then it is 0. It is really a transient input. But these inputs are important, they can occur in control practice. For example, a step input may correspond to a sudden change in one of the variables associated with the system, such as supply voltage or load torque, as we have been seeing for a long time. Similarly, a pulse could be a transient disturbance in the same thing. There could be a sudden change in the supply voltage which lasts only for a short time, goes back to the original value, or a sudden increase or decrease in torque. So, step inputs, pulse inputs are quite frequent and natural in control system applications, not so really sinusoidal inputs. Nobody really wants the motor speed to vary sinusoidally, or motor position perhaps also to vary sinusoidally. In the case of a follow-up system or a tracking system, the output of the system is to follow the input, and the input need not be sinusoidal. Let me remind you about the radar tracking an aircraft and then controlling a gun, so that the gun is directed at the aircraft as accurately as possible. The movement of the target is not at all going to be sinusoidal. So, such responses are quite natural and have to be studied in control system practice. But having spent a lot of time on frequency response, the following question naturally arose, that is there a relationship between these two? For example, if I knew the frequency response of the system, that is, if I knew the amplitude and phase variation for all values of frequency from 0 going all the way up to as high a frequency as you wish, from that input, from that information, would I be able to calculate or determine the step response of the system? And of course, one can ask the converse question, that is, if I know the step response of the system, from that can I calculate the frequency response? And a lot of work was done in this direction, relating the frequency response to the time domain response, or response to a step input or to a pulse input, and so on. That is an interesting topic, but once again we do not have enough time to look at it. But in your system theory course or signals and systems course, you may have devoted some time to this. The frequency response typically would be associated with the Fourier transform, whereas the response to a step input or a pulse input would be typically associated with the Laplace transform. And these two tools are not totally unrelated. As you know, both of them involve an integral, and the integrals also look very similar. So, it is quite natural to expect that there would be some relationship between the frequency response and the time response or the time domain response. So, that is one aspect of a lot of work which was done. With regard to the frequency response itself, you have two parts of it. One is the amplitude variation, the other is the phase variation. And a question that can be asked is, are these two independent of each other? That is, if I know that the gain of the system varies with frequency in a particular way, if I have that curve available, then do I have to separately calculate or measure the phase variation? From the gain variation, can I find out what the phase variation is going to be? So, this was again a subject of investigation, and quite a few results were found out. Of course, much would depend on what kind of system you are looking at. So, if you are looking at a linear time invariant system described by an ordinary differential equation such as we have been studying, then there is a relationship between the gain frequency curve or characteristic and the phase shift versus frequency behavior or characteristic. Of course, in practice, from a practical point of view, if you are determining the frequency response, then it is not more difficult or does not really involve too much work to measure phase shift side by side with gain. So, from the point of view of applying the Nyquist criterion, you can measure the gain and phase variation simultaneously without involving too many difficulties. But there is a theoretical relationship which is useful, and it could be important in some applications. Another line of development was the following. The polar plot refers to kgh, or if in the feedback path we do not have a transfer function, but we simply have a gain, then it is something like kg. This is called the loop transfer function. G is the forward path transfer function, h is the feedback path transfer function, k is the gain in the forward path, and so kgh is the loop gain. But the transfer function of the closed loop from the input to the output, say from the reference input to the controlled output, is given by kg divided by 1 plus kgh. This is the closed loop transfer function, or it is sometimes also known as the overall transfer function from input to output. Now, just as we looked at the frequency response for the kgh part of it, that is opening the loop, applying an input at a particular point and measuring the output at another point, the input being sinusoidal, one could in principle think of the overall control system when the feedback is in place being applied a sinusoidal input, and therefore you expect that the output will also be sinusoidal with a different amplitude and a different phase. So, one can ask, what is the closed loop frequency response? That is the frequency response corresponding to the closed loop transfer function. And of course, then a natural question that will arise is, from the loop transfer function frequency response, or from the Nyquist plot or the polar plot of the system, can one determine the closed loop frequency response? Of course, the answer, one answer is immediate, because Ts is kg over 1 plus kgh. Therefore, when we are talking about frequency response, one way of obtaining it immediately is to replace s by j omega. You get a complex number then in the transfer function, from the transfer function, whose amplitude is the gain and whose argument is the phase shift. Therefore, we have to look at T j omega. This is equal to then k g j omega divided by 1 plus k g j omega h j omega. Now, if I already know g of s and h of s, then it is just a question of evaluating this at different values of frequency omega or angular velocity omega. So, from the calculational point of view, or from the point of view of computation, there is not anything very difficult. This is a simple calculation. Of course, g is itself a ratio of two polynomials. Similarly, h may be a ratio of two polynomials. So, this will involve some complex arithmetic, and then one can find out T j omega as a complex number, and then of course look at its absolute value to get the overall gain, and look at its argument to get the overall phase shift. Now, this is where what I have called an engineering approach or attitude comes into the picture. Of course, it is true that this can be calculated, and today every one of us can hold a calculator in our hand or in our palm for that matter, or we have access to a computer where such or to program packages where in fact the whole calculation will be done at a very simple command. You do not really have to write down any program statements and so on. All you have to do is input appropriate data. So, today there is not a big problem at all, but that is not engineering. Engineering looks at the problem in different ways and in intuitive ways, that is, in ways in which one can see something going on and get a feeling for what is going on. So, some methods were developed. Now, it is easier to work out a graphical method of obtaining the gain and phase shift for the closed loop transfer function from the polar plot, for which the feedback transfer function should be a constant. It may even be 1, that is what is called a unity feedback system, that is the output is directly compared with the reference input as we saw earlier. So, we will assume that h is simply 1, and therefore, we are looking at a loop transfer function which is given by kg divided by 1 plus kg. And what we are now trying to develop or think of is the following. Here is the complex plane in which there is a polar plot. As we saw earlier, the polar plot would depend on the number of poles and number of zeros of the system and their location and so forth. For the sake of simplicity, I am just drawing a simple curve, say a polar plot that looks like this. It could be just some arbitrary polar plot, really does not matter. Each point of this curve is what is a value of g j omega that is each point of this curve corresponds to a complex number. Remember, this is the complex plane, which is the complex number g j omega. So, if this is for some value of omega and I want to find out t j omega at this point, or for this omega, what I have to do is I have to take this complex number, that is g j omega here, then multiplied by the gain k which I have selected, whatever is the value of gain k, and then add to that 1 in the denominator and then calculate this, then take the absolute value and the argument of this whole number. Now, instead of this arithmetical operation, one looks at the following idea. Now, this idea is to be found in many places, not only in engineering but also in physics. In civil engineering, those of you who may have had some idea of what is called surveying and leveling, that is finding the variation of altitude in a given terrain, one talks about what are called contour maps. That is, you look at heights above, let us say, mean sea level or above some benchmark at a number of points in a particular area, and then show them by means of a set of what are called contours. You imagine that you are looking at the portion of land from a satellite, as it were, that is from the top. In other words, it would be what one could call a plan view of the terrain or a part of the terrain, and then all the various points or the various locations, these could be some landmarks, it could be the top of a building, or it could be the bottom of a building, or it could be the top of a tree or the bottom of a tree, and so on and so forth, the various landmarks, or it could be just the surface of the earth or soil. These are points with the same altitude or height are joined by a curve, and these are called contours. And then you have a set of such curves for various values of the height, and such a map is known as a contour map. That is, each curve or a contour is the result of joining all those points which have a given height or altitude. Another contour corresponds to a different altitude, and of course, these heights or altitudes are shown alongside these curves. For example, this may be a height of 100 meters, this may be a height of 105 meters, and so on. Of course, this cannot take care of each and every point in the terrain, and you cannot really measure the altitude at each and every point of a terrain, but it gives you a very good idea of the nature of the terrain. For example, if this is increasing height, then probably there is some kind of a peak here, and this may be the contour map of a part of a hill, for example, where this point may correspond to something like the peak, and then there is the land sloping downwards in all directions. From contour maps we can make out valleys, for example, and so on. So, that is one engineering way of conveying information. Instead of just tabulating graphically, you show it by means of contour maps. In physics, in electricity and magnetism, which you have studied, one has the notion of an equipotential. Again, you are considering a region perhaps which is a part of a plane, and at each point there is an electric potential. Then you imagine joining all those points in the plane where the potential has a given value. If the potential is expressed in, say, volts, then all the points at which the potential is a certain number of volts are joined together to get a curve, and such a curve is called an equipotential curve. Of course, you can talk about an equipotential surface if you are working with three-dimensional region, which is of course usually the case, but it is not easy to show surfaces on a plain piece of paper. So, equipotential lines or equipotential curves can be more easily depicted. So, these are equipotentials, curves along which something has the same value. It may be the height of a point above a certain datum level, or it may be the potential of a point above a certain datum or a reference point. This idea can be used in this case also. In this case, what can be done is the following. We can think of all those points on the polar plot. This is the polar plot. At every point there is a value of g omega and a corresponding value of t j omega, and therefore a corresponding value of the gain. Now, what you do is you look at all those points in the complex plane which will correspond to a given value of absolute value of t j omega. That is what you do, or what you think of is the following. Of course, this is a particular polar plot. I may have another polar plot which looks different for a different system, or if I change k, the polar plot will get scaled. So, think of every point in the complex plane as a potential example of g j omega. It could be the value of g j omega for some frequency omega for some system g. So, every point in the complex plane is a candidate. It can be on the polar plot of some system for some value of the frequency, right. Now, for this value of g j omega, therefore, let us call it simply z. You can immediately think of z as x plus j y if you want in the rectangular form. Now, for this point, that is for this complex number z, I can calculate the corresponding absolute value of t j omega, which will be what, z divided by 1 plus z, absolute value of this. So, corresponding to a given point regarded as the value of g j omega for some g and for some omega for that system, one can say that this number corresponding to it would be the gain of the closed loop system at the same value of frequency. So, now you say, all right, what are all those points or values or complex number z in the complex plane for which absolute value of z divided by 1 plus z is a constant. Of course, because it is an absolute value, it must be a constant greater than or equal to 0. Now, such a set of points can indeed be determined, and this is the transformation really from z to z over 1 plus z or modulus of it. What you are looking at is the set of points z where this function or this transformation has a constant value, which is some positive number. Of course, because it is gain, we can always think of it in terms of dBs rather than in terms of the absolute gain. Now, it turns out that the set of such points lie on a circle. Now, this is something which is not very difficult to prove, and you have done enough in complex variables to be able to prove it. So, you should try to do it on your own. What is it that I am saying? That is, think of a complex number z, look at this equation equal to constant equal to, let us say, alpha greater than 0. What is the set of points z for which this is true? Show that the set of all these points lies on a circle. Now, because this circle corresponds to this constant value, which is the magnitude of absolute t j omega, which is of course the closed loop gain, such a circle is known as an M circle. So, for each constant value, that is for each value of the magnitude of the closed loop gain, you have a circle. One can find out the center of this circle and the radius of this circle. That will of course depend on this alpha, and so you get a family of circles. So, it somewhat corresponds to the contour map. Of course, the contour map shows you the actual height or the potential equipotential show you the actual potential, whereas here these M circles, if I can draw the whole set of them, would then enable me or would give me the value of the closed loop gain at a particular corresponding to a particular point in the complex plane, which may be the value of g j omega for a specific g and a specific omega. So, in other words, once you have these M circles or a number of them drawn on a chart or on the complex plane, on that you can draw the polar plot, and then almost for every point on the polar plot you can read off the value of the gain. Let me illustrate this with the help of the contour map. Now, here is the contour map of a place or of a terrain, and let us say somebody starts moving and the path of that person is something like this. Let us say the person is going in the direction indicated by the arrow. Then what can we say from the contour map? Let us say at a particular moment of time the person was at this place on the hill where the altitude was 100 meters. A little later the person went up a little bit, climbed 5 meters to another place, and still later another 5 meters to a third place, till finally perhaps the person reached the top of the hill. So, here time would be the parameter. As you move along the curve, it corresponds to the movement of the person or climbing of the hill, time is the parameter, for each value of t, the intersection with the contours of the path of the person gives you the altitude or the height reached by the person at that moment of time. Imagine a team or an individual mountain climber climbing the Mount Everest. Now, if you had this kind of an information displayed, you would essentially sort of follow the climb of that person, that is, in 1 hour he climbed so many meters, in the next hour so many meters, and so on. Now, it is something like this in the case of the M circle and N circle. We have the polar plot and we have a set of circles, then we can think of tracing the change in the frequency response as omega increases from 0 upwards, and for the intersection of this polar plot with the various circles, because on the circle, just as on the contour map, along the contour map I have the altitude labeling it, for the M circle I will have the value of alpha that will appear alongside it, and so from this one can read out the change in the gain, the overall gain as a function of frequency, and then if necessary, of course, one can plot it. But as I told you, it is not necessarily always to do exact calculations, to do plots. One can get a qualitative idea of what is happening. So, this is the set of M circles. Now, this was for constant amplitude of the overall transfer function, which involved really the function z divided by 1 plus z, modulus of it equal to constant. Of course, we can do the same thing or something similar for the phase shift, and we can look at angle z plus z divided by 1 plus z equal to constant equal to an angle phi, which of course we will have to let it range over say 0 degrees to 360 degrees, or if you wish minus 180 degrees to 180 degrees, because the argument can vary over a total range of 360 degrees. Now, one can show, and again you should try to show it, that the set of all points z of the complex plane for which the argument of z divided by 1 plus z is a given constant phi, where if phi is interpreted as degrees, in degrees lies between say 0 and 360, is again a circle. Now, because the earlier circles were called M circles, M for magnitude, people called these N circles. So, for each value of the phase shift of the overall transfer function, there is a circle or an N circle. So, there is another contour map, so to speak, for the phase shift. There is a contour map for the gain, and there is a different contour map for the phase shift. And then in exactly the same way, as you move along the polar plot, that is, as you trace the polar plot, function frequency, what is the gj omega at each point, intersection with the N circle will give you the phase shift at that point. So, this is the set of M circles and N circles. You can calculate the location of the center and the radii of these circles depending on the value of the gain alpha or the phase shift phi, and you can actually draw a small number of them. When these ideas were introduced, of course, just as you have now graph paper available or coordinate paper available, and then I told you also that we have a semi-logarithmic paper that is available, people prepared and sold charts containing these M and N circles. So, you had a ready-made set of M circles and a ready-made set of N circles. On those charts, one with say M circles on it, you could plot the polar plot either from experimental data or from theoretical calculations, and then determine the closed loop gain as a function of frequency or get some qualitative idea about that variation. Another chart of N circles would give you the variation of phase with or phase shift with frequency. Because there are some further interesting things. For example, between the M and the N circles there is a nice relationship, and that is each M circle is what is called orthogonal to each N circle. That is, whenever an M circle intersects an N circle, they intersect at an angle of 90 degrees. That is, if you were to draw tangents to these two circles at the point of intersection, the angle between the tangents would be 90 degrees. That is, these two sets of curves are orthogonal to each other. The simplest case of which is not of course closed curve of something like this, a system of lines which are orthogonal to each other, is what? Of course, you are not, perhaps you have been told that this is an example of a set of orthogonal curves. These are not closed curves, but these are orthogonal. They are nothing but the lines on our coordinate paper. The coordinate paper lines are orthogonal, say x axis lines and y axis lines, and there is a whole bunch of them. So, here is an example of a set of lines, the x axis lines, so to speak, and the y axis lines, which are orthogonal to each other. Similarly, the m and n circles are orthogonal to each other. Of course, that is related to something like the following, that is, you have a function of the complex variable and you are looking at the modulus and the argument of that function. Now, it is happening for this function z divided by 1 plus z. So, one can ask, what about a more general function f of z? If I look at mod f z equal to constant, I will get a set of curves, one for each value of the constant. If I look at argument f z equal to constant, I will get another set of curves. Would these set of curves be orthogonal to each other or not? That is a question that one can ask, and it has been studied in some detail. Of course, it is not necessary to have the m circles and the n circles on two different sheets of paper or on making two different charts. We can have them on one and the same piece of paper, although it might become a little confusing, but as I said, the m circles and the n circles are orthogonal to each other, and just as you know how to use the coordinate paper in order to draw a graph, or you would by this time know how to use the semi-logarithmic paper to sketch the Bode plots. So, by practice one can recognize which are the m circles and which are the n circles and use that combined chart paper properly. And as I told you, these things were actually done years ago when these ideas were introduced. Today, of course, you will find it very difficult to get hold of even one copy of this chart containing m circles and n circles, although it is quite easy to make your own chart. And I have told you that you should try to do it for, say, different values of m, 10 different values of m, actually draw the m circles. Similarly, for perhaps 10 different values of n, draw the corresponding n circles. Now, here we use the polar plot just as it was and just entered the polar plot information on the m and n circle chart, and one is able to read off from that chart the closed loop gain and the closed loop phase shift. Now, there was an engineer by name Nichols who had a somewhat different idea, and the advantage of his scheme is that it is more easy to use or more helpful in design. Determining the closed loop frequency response from the open loop frequency response is one thing, and determining what kind of controller should be used in the forward path to achieve a desired performance is quite another. In the second case, when you are trying to figure out what kind of controller one should use, what kind of compensating network one should use, phase lag, phase lead, lag lead, etc., you are going to try out various things, and so therefore you are going to change kGH and you want to see the effect of that on the closed loop performance. So, Nichols had the following idea. In the polar plot, what essentially you have is the complex plane, and each point of the complex plane, say think of it as a number z, is simply nothing but g j omega for some g and at some angular velocity omega. So, here of course, the distance to z has the significance of modulus of g, and the angle made by this vector is the angle or the phase shift corresponding to g. So, when you want to draw the polar plot from, say, experimental data, what you will do is you will determine the gain experimentally, you will determine the phase shift, and then knowing this length of the vector and the angle made by the vector, you will locate the point z corresponding to a given frequency omega, and then you will do it for a number of different points and then join them by a smooth curve, and that is the polar plot. So, this is how the polar plot is actually plotted. This of course can be done on the m-n circle chart paper, so that you do not have to draw it separately once again. So, here we are entering the modulus of g j omega and the argument of g j omega directly as the modulus or the length and the argument of a vector or a complex number in the plane. Now, instead of entering this information this way, we can enter it in a somewhat different way. Now, think of again two axes, but now along one axis what we have is angle or phase shift if you wish, and along the other axis we have what is gain, either absolute gain or gain in decibels. Now, it turns out that, and we will see the reason for that very soon, that the phase shift variation usually will have minus 180 degrees as the central point, and then it will range towards one direction of increasing phase shift and another direction of decreasing phase shift. And like the semi-log paper, you can go up to any value that you like. Of course, with minus 180 degrees at the center, I need to go only up to 0 degrees, let us say here, and up to minus 360 degrees, which is also another way of writing 0 degrees. Okay. So, the phase shift range will be from 0 degrees to minus 360 degrees with minus 180 degrees at the midpoint. And of course, there will be other values of phase shift. For example, here will be the minus 90 degrees and here will be the minus 270 degrees phase shift lines. So, the horizontal axis is going to represent, or along the horizontal axis you are going to represent the phase shift of g j omega. The angle of g j omega will be represented by location in the horizontal direction. The horizontal axis is the phase shift axis for g j omega. Along the vertical axis you will represent the gain, and since the gain may vary from a very small number to a very large value, as we saw, one takes the logarithmic gain or the dB gain. Usually this point, which may be thought of as the origin of this set of coordinate axis, corresponds to 0 dB or absolute gain of 1, that is output amplitude equal to input amplitude. And then you have lines which occur at equal dB increments of gain. So, for example, this may be the 20 dB line, this may be the 40 dB line, and so on. This is minus 20 dB, minus 40 dB, and so on. Okay. So, now you have a graph paper. In fact, one can use the ordinary graph paper. All you have to do is an appropriate scale for angle and an appropriate scale for the dB gain has to be chosen, and you can mark points like this. Now, suppose I am looking at the g j omega transfer function multiplied by k if you wish of a particular system, either from the pole zero diagram or from the experimental data. So, what do I get? I get the modulus of g j omega, which is the gain. I will take 20 log to the base 10, I will get the dB gain, and I have measured the phase shift or calculated the phase shift. So, I get two numbers, the gain, dB gain, and the phase shift. That will determine a point in this plane or a point on this chart. For example, what is this point? This point corresponds to a gain of 20 dB. What is a gain of 20 dB? Absolute gain is 10, because 20 log to the base 10 is the dB gain. So, mod of g j omega at this point will be 10, and the angle of g j omega at this point will be minus 90 degrees. So, this will determine a point in this plane, and now you do this for various values of omega and you will get a curve in this plane. It may or may not be a closed curve, because this is not quite the Nyquist image or the Nyquist contour. This is simply the set of values of g j omega plotted in a different way. Angle of g j omega along the horizontal axis and the gain, the dB gain part of g j omega along the vertical axis. Several points are determined and joined by means of a smooth curve. So, this is a transformation from g j omega to angle of g j omega and modulus of g j omega. This is not that z over 1 plus z, transformation is still z over 1 plus z, but now one is looking at plotting of it in a different way. And now you can ask a question similar to the question that we asked earlier for the gain and phase shift for the closed loop transfer function, where we had the polar plot. Now we have a plot which is no longer the polar plot, and therefore, since Nichols introduced this idea, it is sometimes called the Nichols plot. And corresponding to the contour idea or the constant thing idea for the m and n circles, we can now think of the set of all points in this plane where the x coordinate, so to speak, or the horizontal coordinate represents the phase shift, the vertical coordinate represents the dB gain corresponding to any g at any frequency omega. Think of that as a complex number z now. Z over 1 plus z is the overall transfer function. Think of the modulus of that. Now, that is to be a constant. So, the same closed loop gain to be a constant, the set of all those points on this chart or on this plot will be a set of curves, one for each value of the constant. These curves are no longer circles. They look like ellipses, but they are not quite ellipses, and they are fairly complicated. However, Nichols went ahead and plotted a number of these curves, and after Nichols, then subsequently these curves or the charts containing these curves were obtainable commercially. So, instead of the m and n circles, now you have a family of curves, one corresponding to the modulus of the overall transfer function, the other corresponding to the phase shift of the overall transfer function. I am not going to draw them here because they are fairly complicated and there is no need to remember really exactly what they look like. But you can go through this exercise once again and find an equation for a curve like this. Of course, this is the actual variation in frequency, the set of all those points which correspond to a given gain of the overall transfer function. The point here, its coordinates are what they are. The horizontal coordinate is the phase shift and the vertical coordinate is the modulus. In the polar plot, we are not doing anything like that. In the polar plot, and the reason for calling it the polar plot is that it is as if we are plotting the polar coordinates, that is g j omega is plotted as a set of polar coordinates. Here we are plotting g j omega as a set of rectangular coordinates, the two coordinates being the phase shift and the modulus, and the convention is to have the phase shift along the horizontal axis and the dB gain along the vertical axis. Now, what about the origin of this point of this chart? It corresponds to 0 dB, so a gain of 1 and a phase shift of minus 180 degrees. Now, what is the complex number? 1 angle of minus 180 degrees, that is nothing but the number minus 1 plus j 0, and this we saw was the critical point in the application of the Nyquist criterion. Of course, from this chart where I have shown g j omega as a function of omega on this Nichols chart and I have not shown you the curves, it is not possible to conclude anything about stability immediately, because this is not the image contour of the Nyquist contour. For that you have to look at the Nyquist plot, which is the polar plot. But still, the location of this point minus 1 plus j 0, this point as if represents minus 1 plus j 0, whereas each one of these represents some other point in the complex plane. It is not difficult to think of the relationship between the two. For example, here this curve is going rather far away from this point, whereas there could be a curve that goes very close to this point. This point is the critical point for the Nyquist criterion. So, the same kind of information can also be inferred from this kind of a chart. Such a plot is known as a Nichols plot or a Nichols chart. Now, what is the advantage of this? The advantage is the following. I told you that we have the compensating network which can introduce a gain and a phase shift of its own. So, if I have this g j omega plot, if I now think of introducing a constant phase shift by putting something in the forward path or in the feedback path, a compensating network, now what is going to happen? The g j omega curve will simply shift. If I have a phase shift, the g j omega curve, the gain is the same at every point, but there is only a phase shift. So, if I know the compensating network phase shift, I can plot the new g j omega curve rather quickly. If there is also varying gain for the network, I can take care of that by moving up or down. So, at a given frequency omega, the compensating network introduces an additional gain, let us say, and introduces a phase shift. So, I go to a new point. I can do that for a number of points and I will get a new g j omega curve, which then I can plot. So, the compensating network effect on the closed loop performance, specifically the overall gain and the overall phase shift, can be figured out a little more easily than it would be in the case of the polar plot. So, this is the main advantage of the Nichols plot or the Nichols chart, and this was used by control system designers and of course feedback amplifier designers after Nichols introduced the idea quite some time ago in the late 1940s. And as I told you, commercial charts were available and people did make use of it. Control system designers and of course amplifier designers did make use of these charts for quite some time. Today one can say that these charts have become obsolete in the sense you cannot buy them in the market. You can still buy a semi-logarithmic paper, but Nichols chart and M and N circle paper you will not be able to buy. They are still useful control system design aids, but I wanted to emphasize more the engineering way of looking at things through the help of a set of equipotentials, through the set of control lines, M circles or constant gain curves on the Nichols chart and so on. There is this engineering idea of representing data not in one way, but in several ways. Some are like tables. A table, you would hardly call it a picture. So, there is data representation in a tabular form. I can have simply a table which gives omega versus gain or absolute value of g j omega, and I can have a table, and I can have another table giving the argument of g j omega. And of course, if you are doing an experiment, then this is what you will start with. You will prepare a table like this, say omega equal to 0.1 hertz, 0.5 hertz, 1 hertz, 2 hertz and so on, maybe going up to 10 hertz or 100 hertz. Corresponding gain, in fact you may even have two columns, input amplitude may be kept constant, output amplitude, then gain, then dB gain, phase shift. So, this is the tabular form of the data. But from this it is very difficult to figure out what is going on. In fact, for studying stability we need to plot the polar plot. So, this same information or this information will now be represented in a different form by the help of or as a polar plot. Now, once you have a polar plot, you can try to think about stability, what is going to be the effect of the gain k on the stability and so on. You can represent the information on the M and N circle chart, that gives you something else and something different. You can represent the information on the Nichols chart, and that gives you again information about the closed loop behavior in a different way. So, these are various alternating ways of representing a given set of data, and this is what is helpful to an engineer and the engineering way of thinking, alternate ways of representing the same data, so to speak. There are some good points about a particular representation, that is, it helps you to do this operation or that operation, or it gives you this aspect or that aspect more quickly than some other representation. But one should learn wherever possible a number of representations of data depending on the various aspects of the problem that you are studying. And this is my main reason for really talking about M and N circles and Nichols chart right now. We do not have time to go into all the details as to how M circle, N circles, Nichols charts can be used in design. I am stressing the engineering idea of alternate representations of data. That is what is very important to learn and make use of whenever possible.